In this problem, we will find the magnitude of two negative point charges from the origin and the electric field direction due to those charges. First, we want to draw a diagram of the point charges on the x and y axis. And because the electric field has magnitude and direction, we will put vectors in the diagram to show the direction due to the charges. We are using a positive test charge at the origin for this problem, and the charges are negative, so the vectors will be going towards the point charges. Opposite charges attract. Now that our diagram is labeled, we want to convert our measurements into SI units. 1 nanocoulomb is equal to 10 to the negative 9 coulombs, and 1 centimeter is equal to 0.01 meters. This makes canceling out units easier when we are solving the equations. With our numbers converted, we can use Coulomb's law equation to calculate the electric field strength of each point charge. We first find the electric field strength for Q1 at the origin by plugging our numbers into the equation. E is for the electric field strength, K is Coulomb's constant, Q is the charge, and R is the distance squared. We want to keep our answers with 4 sig figs here because we want to show that EQ1 is exactly twice the magnitude as EQ2. Plugging our numbers into the equation, we find EQ1 to be 5.619 times 10 to the 4th newtons per coulomb. We then calculate the electric field strength for Q2 at the origin using the same equation. We see that EQ1 is 5.69 times 10 to the 4th newtons per coulomb, and EQ2 is 2.809 times 10 to the 4th newtons per coulomb. We also see that EQ1 is exactly twice the magnitude of EQ2. Now that we know both the magnitudes, we can adjust our vectors to represent the electric field strength for each charge. I already did this before the video for simplicity purposes. With having both magnitudes of our charges in the electric field, we need to calculate the total magnitude at the origin. We can add the results from EQ1 and EQ2 for this. And because the magnitude of an electric field is produced by a point charge, with the charge magnitude of Q at the point a distance away from R, we need to square both when we add them. We get a total magnitude of 6.28 times 10 to the 4th newtons per coulomb. Taking our magnitudes from earlier for EQ1 and EQ2, we want to draw a new diagram to find the direction. We can use vector addition to find our angle theta by moving EQ1 and EQ2 to their opposite sides. We use SOHCAHTOA here to calculate the angle theta. We want to use tangent and take the opposite side of theta divided by the adjacent side of theta. So we divide EQ1 by EQ2, and then, using inverse of tangent, we get the angle of theta as 63 degrees. Because we are finding the direction from the positive x-axis, we need to add up all the degrees counterclockwise to our line. We add 180 degrees plus 63 degrees, giving us a total of 243 degrees. Our final magnitude and direction are 6.28 times 10 to the 4th newtons per coulomb at 243 degrees.